Hi, this is Adrián Gadrán from Bournemouth University. I'm going to present today our recent work on Polyp Segmentation. We do this with something that we call double encoder-decoder networks. And this is joint work with Gustavo Carneiro from University of Adelaide in Australia and Miguel Ángel González Ballester from the Pompeu Fabra University in Barcelona. So this is going to be a very brief version of our work. I'm going to give a longer talk in the workshop next week, but I will try to convey the fundamental ideas in this short version. So imagine you have your task is to segment these polyps from this kind of images, okay? And you don't know what it is, what a polyp is. So you take a guess. And maybe because you don't know how a polyp looks like, you produce this segmentation, this candidate segmentation, and it's really not so good. As you can see here below, you have the manual delineation of the actual polyp. Okay, and the idea here is that if you were a neural network, what you would do now is you would update your weights, the weights of your architecture, with a loss, an error function on each pixel, and then you would propagate that, and you would update your knowledge of how to solve this task. Okay, so the point here is that if you do this, you would kind of need to wait until the next epoch. So you would need to see all your training set before you get to see this image again. And what we want to do is we want to use actual immediate feedback here. We want to take our error function and we want to reuse it just there to improve our second guess, which would be better. So this way, we wouldn't have to wait until the next time we see this image to get a better idea of how to segment it. Also, this is nice because if we get this first estimate, it's not very good, but it's still quite reasonable. We can use that as a guide to understand where are the areas of the image where we should focus to get a better segmentation. So we can focus on difficult areas in the image. How can we achieve this? So imagine you have a friend that's helping you to solve this task, and your friend gives you an opinion. This is her first estimate of what the polyp looks like, and you take this and you use it together with the original image to produce a second segmentation. So what you do is you take X, which is the original RGB image, you use it together with the estimate of your friend, which is E1 of X, and you use that to pass it through a second network, which is your knowledge of the problem, to produce a better segmentation. A couple of important details here is we are using the output of E1, which is the raw logits of the network, okay? And we are stacking it channel-wise with the original RGB image. So in this case, we will get 4 channels. And then notice that we can also apply supervision, like a cross-entropy loss, for instance, in the intermediate step and also in the final step of this process. In terms of code, you can see that this would be what a single encoder-decoder network would look like. So you have input channels would be 3 because you are working with RGB images, and the output channel would be 1 because this is a binary segmentation task. And then you just simply take X, which is the original image, and you produce a result. If you want to turn this network into a double encoder-decoder network, this is very easy. So you just you build 2 encoder-decoders. And then once you receive the image X, you pass it through the first encoder-decoder, you get X1. And then you use X1 concatenated with X to build the output. And you return both. You return X1 and out because you are going to compute the loss function on both of them so that you can get a better update of the parameters of your double network. In our work, we compare many different options for encoders and also for decoders. It's better that you see the details in the paper because this is kind of technicalities and not really very interesting. This again is some training details, how we train all our networks. So I will leave you to read this in the paper, or I will explain more details in the longer oral presentation. This is the data we use for seeing if this was a valid idea for validating our method. So we have 2 different families here. The first one is the 2 first datasets, CVASID and CBC Clinic. We use this as a training set and also as a testing set. So we separate part of this for testing purposes. But we also use 3 different datasets, which are here in green, which are independent, much different images that allows us to check up the generalization ability of our network. The first conclusions are here in this table. where we compare the performance in the test set of the corresponding to the training set of the single encoder-decoder networks when comparing them with double encoder-decoder counterparts. And we see that in almost all cases, the simple implementation of a double encoder-decoder on top of the single encoder-decoder gives you already a boost in performance all around. So you jump like almost between half a point in dice score here in the UNet combined with MobileNet, up to 2 points of dice score here when you combine FPNets as decoders with dual path networks as encoders. Now, if you want to compare this approach with the state of the art, we used this recent work, which is called PRANET, from Mikai last year. And we used this because they were training on exactly the same data splits and training sets. So it's a very fair comparison. And we compared this, and we realized that we are kind of beating the state of the art by a very nice margin. So it's like kind of 1.5 extra dice score points in the test set of Kvasir, and like more than 1 point of improvement in the CBC clinic test set. And it gets better because if you go to the independent test sets, which contain images that are very, very different from what we were using for training, we see an increase in performance that is much more noticeable. Like in this ETIS, which is the most challenging dataset here to test on, we see an increase in dice score of almost 12 points compared with the best method that we found here, which is this PRANET. And it gets also better in other test sets. So just to wrap up this quick version of our presentation, we are proposing here, this has been used before in different papers, but I don't think this has been used for polyp segmentation. So we are introducing double encoder-decoder networks for polyp segmentation purposes. This works as an attention map that allows you to improve performance with very minimal modification of your code. We've shown here that it provides a boost in performance when compared with single encoder-decoder, and it also attains a state of the art both in terms of the training set that you are using, the test set associated to the training set that you're using, and also in independent test sets. So thank you for your attention, and please come and watch me explain this with more slowly in the workshop if you have the time. Thank you very much for your attention. Thanks. Bye.